Okay, so here's K-9. We're gonna find the area between two curves. Okay, so we're gonna use these two formulas. If the graphs pass the vertical line test, and I'm gonna explain all of this, we're gonna use this formula. So to get the input of the integral, we do top minus bottom, and then everything is in terms of x. If the graphs pass the horizontal line test, we're gonna use this one. The input of the integral, we do right minus left, and everything is in terms of y. Okay, so guys, let me talk real quick about in terms of x versus in terms of y. So here I drew a line, okay? And let's say the equation of this line is y equals 4/3 x plus 6. That is the equation of the line in terms of x. But if I take the same exact equation and I solve for x, which I did right here, I solved for x. So I solved by just multiplying every term by 3 to cancel the denominator, and then I, just got x by itself. This is the same exact equation in terms of y, all right? So these are two ways of representing the same line. Usually we do everything in terms of x because, that's just more convenient. But sometimes here, yeah, for many reasons, more convenient. But sometimes in these problems, we're going to want to take the equations that we're dealing with, which we won't be dealing with till next phase, and rewrite the equations in terms of y. Okay, so let's do this. So we're going to label the red graph F and the green graph G with the appropriate input and output variables. So use the integrals to express the area bounded by the curves. Okay, so I will show you how to do this. So first we got to figure out which test these graphs pass. Oh, and by the way, when we're finding the area between these two curves, I want yellow highlighter. Okay, you look for the intersection points of the curves, which are here and here. And those intersection points are going to be, think of them as like the vertices or the corners of the shape whose areas you're finding. So if these are the corners of the enclosed shape, it's this. So we're trying to find this area. Okay, then you take a vertical line and you ask yourself, for every vertical line that passes through this region, are the graphs only hit once? Okay, so we want the red graph and the green graph to only be intersected one time each by this vertical line. Yep, the red and green are only getting intersected just once by the vertical line. So that means that the region passes the vertical line test. Now it doesn't, sometimes they'll pass both tests, but the reason it doesn't pass the horizontal line test is if you start from down here and you're going up, okay, the red and the green, they're only each getting intersected once. They're only each getting intersected once still. But when I get up toward the top, if you look at this, guys, it's really subtle, but that red graph is getting intersected twice. So that means it does not pass the horizontal line test. Okay, so I'll say vertical line test, check. So I want everything in terms of x. Okay, so when I go to express the red graph and the green graph as f and g, I'm going to go like this. Okay, so this is the red graph. So this is going to be y equals f of x. And the green one is going to be y equals g of x. Okay? So that's like this. All right, in terms of x, like that. If it were in terms of y, we'd want this. We'll do one of those soon. Okay, and then, so we know we're going to have this top minus bottom formula. So I'm just going to write down the formula. So we're going to have from x equals a to b, and usually we just go t minus b dx. All right, now we just got to fill this in. So this is an x interval. So what is the leftmost x value? -8. What's the rightmost x value? 5. So this is going to be the integral from -8 to 5. You don't have to put x equals down there if you don't want to. All right, now for the top minus bottom. So I'm just going to draw a vertical line somewhere. It could be anywhere. And then I'm going to go like this. That's the top function. That's the bottom function. So the top function is the red one. It's f of x. Minus the bottom function is the green one. It's g of x. And that is the answer. Okay. All right, we're going to do 2 more, guys. All right, so this one. So what test does this, okay, so well, let me first find the region. So you look at the intersection points of the graphs. Those are like the corners of the bounded region. All right, so that's the area that we want to be representing with the integral. Let me try the vertical line test. It does not pass. Immediately, I'm hitting the red graph more than once. Let's try the horizontal line test. Yep, I'm only hitting each graph 1 time. Okay, so it is the horizontal line test. So horizontal line test, check. I want, okay, so I want in terms of y. Okay, so when I am labeling my graphs, so the red one, remember the red one is f, this time it's going to be x equals f of y. X equals f of y. So it's like you solved, you took the equation and you solved for x instead of solving for y. Okay, so in terms of y. So x equals the function in terms of y. Or it's not even a function actually, because it doesn't pass the vertical line test. But okay, and then this one here, guys, this line right here, that's going to be g, so x equals g of y. Okay, and I'm going to use this formula. The integral, let me try to focus this. That's better. The integral from y equals a to b, right minus left dy. Okay. Okay, so you're going to let's do a horizontal line this time. Put a dot there and a dot there. Right, left. Okay. The integral from, what's the lowest y coordinate? The lowest y coordinate is -10. What's the highest y coordinate? +10. Now the right function is g of y, minus the left function is f of y, dy. Okay, that's the answer. All right, one more. We're going to do one with an intersection. Okay, so this time, guys, you look at the intersection points. I've got 1, 2, 3 intersection points. So the area we're looking for is actually the sum of these 2 regions. All right, because these 2 intersection points, those are like the corner of this region, the corners of this region. And then these intersection points are the corners of that region. All right, so we really need 2 areas. So our integral, we're going to need actually 2 integrals for this. All right, let me check the horizontal line test. Nope, it's immediately failing. Right there, it hits the red graph twice. I hit the red graph twice, okay. So vertical line test. Yep, I'm just hitting each graph 1 time. Just hitting each graph 1 time. Okay, so I want in terms of x. All right, so vertical line test. So vertical line test, check. All right, So I'm using this formula. From x equals a to b, top minus bottom dx. Okay. Now, guys, if you've got two regions, if you've got like two regions that are part of the entire area, so you want to use like two lines. Like, you know how here I did a single vertical line to figure out the top and the bottom. Here I did a horizontal line to figure out the left and the right. I'm going to do a vertical line here, a vertical line segment, top, bottom. Now, the reason it's important to use two of them is because watch this, guys. On this whole region, the red one's on top and the green one's on the bottom. But then after this intersection point, the top and the bottom switch. So now the green one is on top and the red one is on the bottom. That's why we're going to need two integrals. Okay, so for the first region, it's going to go, okay, so the leftmost x is -8 up to 2, because that's the rightmost x. Oh, I forgot to label. Okay, so this is y equals f of x, and then y equals g of x. Okay, so top minus bottom. The top one is f, the bottom one is g. So f of x minus g of x dx plus the integral from 2 to 10. Right, those are the x values. Top minus bottom. This time, the top one is g, and then the bottom one is f. Okay, and that's it.